Hello everyone, welcome to the course Material Characterization with course ID NOC 26MM43 and being taught by Professor S. Shankar of IIT Madras. So this is the live problem solving session for week 11 of the course. My name is Mayank Goyal. I am a research coordinator Department of Electrical Engineering IIT Bombay. This course is being taught by Professor S. Shankaran, who is an associate professor at the Department of Metallurgical and Materials Engineering IIT Madras. The course plan for this week is diffraction and image formation, various imaging techniques and spectroscopy. With the so this problem like session is happening every Sunday 6 p.m. to 8 p.m. at the school meet link. So first I will give you an overview of this week's topics. So we are studying TM. So in TM, so we are taking a very thin 3D specimen, and the interaction between electron and the specimen are in 3D. So it is yielding true 3D interactions, but the but what we are seeing are 2D patterns. So all the 3D data gets averaged and collapses into a 2D projection, which we see on the fluorescent screen. And and the and our purpose is to reverse engineer this precise projection into 3D data. So typically two types of diffraction are used. One is selected area electron diffraction or SAD or SAED. Another is CBED, that is convergent beam electron diffraction. So in selected area diffraction we use a parallel beam which which produces very sharp zero order diffracted spots. Whereas in CBED we use converging beam with very large convergence angle greater than 20 milliradians, and it results so it, due to this the diffracted spots change from single points to large discs, which are called causal Molenstad patterns. And since it's convergent, so the probe size reduces. It goes to much lower than 1 micron. Hence why it's called a nano probe. So you can see here as the convergence angle is increasing from -2 to 8.1 milliradian, each spot has increased in size to become a disk, which is now overlapping. But first, we talk about how do we are defining the probe diameter. So the probe diameter is TM physically refers to the full width at half maximum of the beam's intensity profile. So it take the intensity profile of the beam spot and you take the full width at half maximum. So you take the you take the point where the beam is at half intensity and you take the full width and you call that your beam's probe diameter. So if you let's say you have your normal probe, you may have a probe diameter of around 40 nanometers, after reaching 40 nanometers. But for doing STM, you use nano probe where your FWHM may be 4 nanometers. And if you want to do high resolution STM, there your FWHM may be 1 to 2 nanometers. So smaller spot sizes drastically narrow the FWHM, allowing for atomic level spatial resolution in high resolution STM mode. Next would be our camera length calibration, RD equals to lambda L. So it's derived using from Bragg's law. So Bragg's law will give sin theta equals to lambda by 2D. And since here the theta is extremely small, we can approximate sin theta equals to theta. So theta is approximately equal to lambda by 2D. And if you take the projection, if you take the projectionometry, R, you will get R by L, where R is your distance from the center to on to the spot on the screen, and L is your distance between specimen plane and a detector. That equals to R by equals to tan 2 theta. Again, theta is very small, so we assume tan 2 theta equals to 2 theta, and then we equate both of them. We get R by equals to lambda by D, which makes it RD equals to lambda L. So, so from here you can calculate your interplanar spacing D using the using the distances on your screen. So R is your distance from center to diffracted spot, which is what you will measure. D is your interplanar spacing. Lambda is your electron wavelength, and L is your camera length. That is distance between specimen plane and a detector. So one warning. So the camera length is a projected length between the magnification, and it is not the true physical length inside the TM. So it is not the actual length between specimen plane and detector. It will be based on magnification. The length will be scaled accordingly. Now so the diffraction that we are getting is gives us the detail about the reciprocal space. So you have the real space where you have your interatomic distances that will result in a reciprocal space with certain spots. So the spot size in the distances in reciprocal space are inversely proportional to the distances in real space. So if you have a if your interatomic distances are smaller in real space, your in reciprocal space they will be the spots will be much more spread out. So the distance between spots in a diffraction pattern holds an inverse relationship to the periodicity of the object. As the physical lattice shrinks, the reciprocal lattice expands. Hmm. So now how do you map 3D orientation into two dimensions? So we use stereographic projection. So an angle through 2D projection of 3D planes that so just like how we Earth is round, but in a map we see a projection of the Earth which is true to its area. So by measuring the angle between poles, we can identify crystal orientation entirely in 2D such that between 100 and 010 there will be 90-degree angle. Between 110 and 010 there will be a 45-degree angle. Then zone axis, so the Y zone law. So when a number of planes are parallel to a single direction, they constitute a zone, and the common zone direction is called the zone axis. So the zone axis is common to all the planes, and it lies in the center. And around this, each family of planes will create a each set of planes will create a zone circle, which will satisfy the equation HU plus KV plus LW equals to 0. So the indices HKL of all spots in a diffraction pattern are mathematically related to the indices of the zone axis, which is given by UVW, to which the electron beam is parallel. And how the diffraction is happening, this we had already studied earlier. So diffraction happens when Ewald sphere intersects with the lattice points. So the Ewald sphere geometrically links the reciprocal lattice to Bragg's law using the vector equation G equals to K minus K naught. So a diffraction spot will only appear if its reciprocal lattice point exactly intersects the two-dimensional Ewald sphere of surface of the Ewald sphere. So now how the wavelength impacts this. So in X-ray diffraction, the so the Ewald's we had studied that the Ewald sphere radius is inversely proportional to wavelength. So in so the electron wavelengths are two orders of magnitude smaller than X-rays, and because the wavelength is small, 1 by lambda, which is the radius of Ewald sphere, is massive. So the sphere's surface is essentially flat at the micro scale. So when we are looking at very few spots, it's almost as a flat, which allows it to satisfy Bragg's condition for many reciprocal lattice points at once. So it allows us to see a dense multi-spot TM pattern instead of a instead of few spots. Instead of few spots, we get Bragg's diffraction from many multiple lattice points, which creates a dense pattern. And why do we get circles as spot? so so because the specimen is thin, the mathematical reciprocal lattice point stretches into a rod which is called railrod of length 1 by t. So if your real specimen is of distance t, your reciprocal lattice point will stretch into a railrod of length 1 by t. And when the 2D surface of the massive Ewald sphere cuts perpendicularly through this 3D rod, the resulting geometric cross section is a circle which forms a spot we see on the TM screen. So this Ewald sphere, when it crosses this railroad, it will result in a circle. And now what happens if we have single crystal or polycrystalline structure? So in single crystals, so each lattice point is at a defined position. So each lattice point in the refraction reciprocal lattice will be at a defined position. So we will get perfectly aligned spots. But in polycrystalline lattice, we are the lattice points are not at defined positions; they are randomly distributed. So they will result in circles, which we had studied earlier as the zone circles. So instead of fixed lattice points, we will get circles with each satisfying the HU plus KV plus LW equals to 0 equation. So if the aperture selects an area with many randomly oriented crystals, the diffraction patterns become the sum of all individual spot patterns. So for each orientation, the spot pattern will be slightly different, and all of them will get summed because it is averaged over the whole thickness and region. So all the orientations will combine into a circle. So the individual spots fall so close together across all 360 degrees that they merge into a continuous concentric rings. Now, higher order Lau zones. So if beam is parallel to the zone axis, then we get a proper pattern. But if the crystal is slightly tilted, we get some fringe patterns which are called higher order Lau zones. So by slightly tilting the crystal in CBD mode, the evolved sphere geometrically intersects the next layer of the reciprocal lattice in 3D space. This reveals the first order Lau zone, unlocking higher level symmetry and depth data hidden. So if it's parallel, we are only seeing the zeroth order diffraction. But then if the sample gets tilted, we also see first higher order diffractions, which which is given by your higher order Lau zones. So next is calibration standard. So so since lattices are spatially symmetrical, a 180-degree rotation will yield opposite index signs, but it will still give, but the lattice will look similar, diffraction will look similar. So we must carefully cross-reference to fix the correct indices. So you can see here, gold and aluminum can be used for calibration. So they are very standard FCC metals. With gold have a interatomic spacing around 0.418 nanometer. Aluminum will have around 0.41405 nanometers. And we see which ring number will correspond to which family of plane, which set of plane, and from that what will be the interatomic spacing, which is then used to calibrate your calibrate your camera constants and all. So to get diffraction, we have to first fix the hardware and the signal. So that is, we have to do calibration. We have to correct the beam shape. If for SAD or CBD, do camera lens calibration. RD equals to lambda L. We have to then look at the real image to see the reciprocal lattice and stereogram. So if we are getting smaller, larger diffraction spacing, that would mean smaller real spacing. So and stereograms provide angle through 2D mapping of 3D poles, and then we use Weiss zone law, HU plus KL, KV plus LW equals to 0 to get our set of planes, and then we use the geometric understanding to get resulting. So the evolved sphere, so the interaction is due to the diffraction is due to interaction between evolved spheres and Bragg's law, with where the spots only appear when sphere cuts through the railroads, which and the electron wavelength is yielding a massive sphere radius, which means eliminating dozens of spots simultaneously. So the vector parameter S measures the exact quantitative deviation of a reciprocal lattice point from the perfect Bragg angle. So in reality, there should not be any deviation, but so in ideal condition, there won't be any deviation, but in reality, we have some deviation. It can be positive deviation or negative deviation, and that is given by the vector S. So you get G dash equals to G plus S, and controlling the S is the key to create precise contrast for detecting images in advanced microscopy. So we have to control the S. Then we talk about Kikuchi diffraction. So in standard so in standard TM, where we have a very thin sample, the light will pass without any scattering and create precise spots. But if we have a thicker sample, then we will have Kikuchi TM, where there will be scattering of the electron beams, and that will result, instead of spots, it will result in Kikuchi lines. So Kikuchi lines require a relatively thick sample with a low density of crystal defects and inelastically scattered electrons which have lost energy and create a diffuse background are subsequently elastically scattered by lattice planes to form lines. So first, due to thicker thicker sample, there will be an elastic scattering, which are then elastically scattered by the lattice planes to form these Kikuchi lines. And then Kikuchi line results in two parallel lines, ray 1 and ray 2. So the ray 1 would be the axis line, so it travels closer to the forward direction and carries higher intensity. So when it arrives at the back focal plane point B, it creates an excess of electrons over the background, which will result in bright line. And the deficient line, which travels further from the forward plane and carries low intensity, it creates a deficiency of electrons at point D and results in a darker line. And the spatial separation between these two perpendicular lines should be parallel lines. These two lines, parallel lines, represents the G vector. And then how the Kikuchi lines are formed. This also we have studied earlier. It uses causal cones and parabolic interaction. So the diffracted rays will form causal cones from a semi-angle with a semi-angle of 90 minus theta. And this when these causal cones interact with the flat 2D detector screen or Ewald sphere, they mathematically form parabolas. And because the angles involved in electron diffraction are extremely small, the parabolas have very massive radius, and which means in the region where we are seeing them, we see them almost as a perfectly straight line in the resulting diffraction pattern. And the separation between two sets of two resulting pair of lines is exactly 2 theta. So what happens with dynamic tilting? So if we have negative deviation from the Bragg's angle, the specimen will appear brighter. They will be brighter, no, where or even with positive deviation, we will have brighter zones. But if there is no deviation at exact bright condition, we will have very high contrast and we'll have single set of lines. So tilting a specimen by a small angle alpha changes the intensity of the diffraction spots, but physically shifts the position of the Kikuchi lines by a distance r equals to L alpha, where L is your camera length. So by setting up a two beam condition where only one set of planes is strongly diffracting and ensuring s greater than 0 is critical for imaging a structure diffraction like dislocation or sagging faults with maximum contrast. So according to the set of planes will have different geometry, different symmetries. So like germanium 111 zone axis will result in a 3/4 symmetry, whereas as magnesium 001 zone axis will result in a 6/4 symmetry. So the Kikuchi lines are highly rigid, are rigidly tied to the crystal lattice and act as the ultimate tool for precise orientation mapping, and by matching intersecting bands to stereographic projections, we instantly deduce point group symmetry and lock the beam to a specific zone axis. So we studied this that in standard TM we use SAD where we use parallel beam and we get individual spots, whereas in CVD we the light converges on your sample and then it diverges, resulting in ex- discs instead of spots. So while probing a microscopic spatial volume in real space, the convergent beam excites a massive volume of reciprocal space. This allows the microscopist to detect true 3D symmetry from flat 2D screen. Then we go to higher order Lau zones. So Zols, which is zero order Lau zone, is this its central flat 2D projection, typically a standard diffraction. It captures horizontal plane data. And then first order Lau zone is your first concentric ring. It gives the z-axis data by revealing reciprocal spacing along the vertical axis. And if we want to go even deeper, we go to second order Lau zone, which is wider and fainter outer ring and captures deeper 3D data. And the governing geometry for a first order Lau zone is h star equals to g1 squared lambda by 2. So we have h star equals to n by r uvw, where r uvw is the zonal repeat and n accounts for symmetry lattice absences. So if you have a primitive lattice or a rhombohedral lattice, n will be equals to 1. If for face centered, n is equals to 2. If u plus v plus w is even, otherwise n is equals to 1. For body centered, n equals to 2 if u, v, w are all odd, otherwise n equals to 1. For base centered, n equals to 2 if u and v are both odd, otherwise n is equals to 1. So half spacing or displaced repeats in the higher order zones physically prove the existence of internal glide planes which are perpendicular or parallel to the projection, And this definitely separates true 3D geometries from flat 2D approximations. So if you see in spinel, which is ZnL24 with space group F3DM, we notice that the spots spacing along X star and Y star in outer FOLG ring is actually half the spacing of the central zero order Lau zone. And in synthetic MgGO3, we see that monoclonic lattice structure for FOLG is displaced by exactly half a repeat in the X star direction. So both this half spacing and displaced repeats is resulting in guide planes, so which gives you three-dimensional data from not so instead of just your average 2D approximation data. So you have advanced diffraction, you have Kikuchi diffraction, which uses parallel beams. Convergent beam uses convergent probes, which are micro and nano probes. In Kikuchi diffraction, inelastic scattering followed by elastic Bragg diffraction, whereas in convergent beam, complex elastic excitation of multiple laws simultaneously. In Kikuchi diffraction, the relate sample is relatively thick and has low defect density, whereas here it will depends on the probe size and what the interaction volume is required. In Kikuchi, we get parabolic bands which appear as straight lines, and in convergent beam, we get concentric rings which in each is composed of individual diffraction disks. In Kikuchi, we get we use Kikuchi for precise orientation mapping and generating zone axis maps by setting two beam conditions. And for in CVD, we use is used to determine exact specimen thickness and 3D crystal symmetry and exact lattice parameters. The core principles that for remembering is that the tilt here is to change the contrast and not position. So tilting the specimen shifts the intensity of your spots, but it physically moves the Kikuchi lines across your screen. So it is used to get the positive S parameters for maximum defect contrast. And by tracing the so looking at the bright and dark line, the exact midway of the bright and dark line is your G vector, and using CBD we can instead of looking just at the zero order diffraction, we can look at higher order diffraction to map a 3D structure. So TM is also used to see microstructures. So to the untrained eye, a bright field TM image is a chaotic mix of light and shadow, whereas it is a precise map of electron interactions. Why do some grains appear perfectly dark while the next one is glowing, and what is causing the rippling zebra type patterns across flat surfaces? So every gradient, fringe, and shadow in this image is a direct physical result of amplitude contrast, and we must first track where the electrons to understand the image. So how amplitude contrast is generated. So contrast arises from local variations in diffracted beam intensity. So the objective aperture acts as a physical gate which can be used to isolate specific construction. So in bright field it captures only the diffracted beam and the diffracting regions will appear dark, whereas in dark field it will capture only one of the diffracted beam and the other all other regions will appear dark, and this single direction diffracting region will appear bright. So there are two diagnostic frameworks: kinematical theory and dynamical theory. Kinematical theory assumes independent beams, whereas dynamical theory assumes coupled interfering beams. Kinematical theory it works for extremely thin foils, whereas dynamical theory works for thicker perfect crystals. In kinematical theory works away from exact Bragg positions where S is not zero, whereas dynamical theory works at exact or near exact Bragg position. And in kinematical theory we are looking at primary extinction, that is T naught equals to 1 by S, and in dynamical theory we are looking at the extension distance epsilon g. So while kinematical theory offers a foundational understanding of isolated diffraction events, dynamical theory is required to decode the complex interfering intensity oscillations that is observed in real samples. So in kinematical, the baseline is your psi psi square d equals to f by t square sine square pi t s by pi s square divided by psi t square equals to 1 minus psi d square. So it has assuming two beam. So kinematical theory assumes only one transmitted beam and one diffracted beam existing, and there are zero secondary interactions. So T is your specimen thickness, S is your deviation parameter, and F is your structure factor. So the equation perfectly sum to 1. Therefore, kinematical theory predicts that bright field and dark field images are exact optical components. Inside a perfect crystal, the periodic potential of the atomic lattice causes high energy electrons to dynamically transfer back and forth between forward scattered and diffracted wave functions, and this defines the epsilon g, which is exact physical depth required for wave amplitude to transfer back and forth once, and epsilon g is equals to pi v by lambda fg. So at integer multiples of epsilon g, all electrons return to the transmitted direction. At odd half multiples, they end up in the diffracted direction. And this results in coupled oscillator model where we have scattering from the undeflected beam as well as scattering from diffracted beam, and this is defined by Pauli-Whelan equations. Dynamical diffraction is perfectly analogous to two coupled harmonic oscillators periodically exchanging all their vibration energy. These these equations map the variation of wave amplitudes as a function of depth z. They mathematically prove that the amplitude of each wave changes progressively due to a continuous contribution from the other. Hmm. So why do adjacent grains in a flat specimen display starkly different solid contrast and bright field? The cause is crystallographic orientation. So the deep black grains are oriented perfectly to diffract strongly. Because the objective aperture blocks the diffracted beams, the intense signal is lost, rendering the grain dark on the viewing screen. So in the light region, diffraction is weak. In the dark region, diffraction is strong. And what happens at the edges? So at the edges of electrolytically polished holes, specimen thickness slopes sharply. As the electron beam traverses the wedge, it cuts through varying depths of internal intensity oscillations. Each time the local thickness equals a half multiple of epsilon g, where transmitted intensity is at a minimum, a dark band appears on the 2D bright field image. This by counting fringes, we can calculate the exact local thickness. So if we have a wedge shape at so if we have a hole in your sample, there will be a varying thickness, and this varying thickness will result in fringes between dark diffracted beam and undiffracted beam, and that by counting these fringes we can get the other thickness at the region. So now what happens if your sample is bent? So unlike wedge fringes driven by changing thickness, bend contours are driven by changing orientations at a constant thickness. So now you are not changing your thickness, you are changing your orientation. So as the foil bends, the local lattice planes rotate in and out of the exact Bragg diffracting condition. So when S approaches zero, dynamic diffraction peaks, casting thick black sweeping black contours onto the bright field image. Mhm. So fringes do not appear only at physical edges; they appear wherever an inclined planar defect, such as stacking, fold, twin, or grain boundary, disrupts the lattice. So the boundary plane acts as a phase-shift interface, and because the interface is angled, the vertical depth periodicity intersects it at continuously shifting points. This will result in fringes, and the number of resulting fringes depends strictly on the extinction distance of the operating reflection. So the total diffracted intensity is the summation of individually diffracted wavelets from unit cells at increasing depths. So, so we have a thickness of lattice. So from the diffraction will come from every lattice, and there will be multiple diffractions. So the total diffracted intensity is equals to the sum of individual diffracted wavelets from unit cells. So you get pi s equals to summation fg exponential plus I 2 pi s into rg. So instead of computing endless equations, we use a geometrical analog, the phase amplitude diagram. So each wavelet is a short vector, and we link all of them together to map the total intensity shift across the depth of the crystal. And this can then come from spiral. So if s is greater than 0, we will have very huge spirals, which will result in large shifts in your large shifts in intensity with thickness. And if s is much higher than 0, then all the all the spiraling is constricted to smaller region, and the change in intensity with thickness is much lesser. So the geometry of the spiral instantly predicts the visual contrast. So as we change the thickness, winding further along the path of the spiral, the intensity oscillates as the vector wraps around. And if we change orientation, we are shrinking or expanding the radius of the spiral. A smaller is that is closer to Bragg angle creates a large phase amplitude circle which generates massive phase shifts and starker contrast in the image, whereas large S will result in lesser contrast. So the contrast variation, which is amplitude, can come from three things. One is change in thickness, which comes from pits, holes, or electrolytic edges, which gives wedge fringes. It can come from change in orientation, which is bending foils on sub-boundaries, bend contours. And it can come from change in structure composition. For example, composition changes. Example of composition changes are spinodal systems. Example of structure changes are martensite. Example of orientation interface is coherent incoherent precipitates grains twins. So every observable phenomenon in a metallic foil can be traced to a local perturbation in T, S, or G. So if we are seeing solid black white grains, it comes from differential lattice alignment, and it's driven by your orientation, and the governing framework is kinematical. If you are seeing parallel zebra stripes, it is coming from wedge shaped physical slope, and which is due to thickness change. And it is governed by dynamical framework. If you are seeing symmetric swirls, it is coming from foils bowing under stress, and it is coming due to deviation from Bragg angle, and it's governed by both dynamical and kinematical framework. And if you're seeing internal banded lines, it is coming from tilted planar phase shifts, which is inclined interface, and it is again dynamical framework. So how to decode the beam? So if an electron beam passes through a perfect defect-free crystal, the screen will show only bright featureless illumination because contrast requires physical interactions, defects, inclined surfaces, or varying mass to perturb the beam. So diffraction contrast comes from crystal orientations and Bragg conditions. Then mass thickness contrast comes from change in atomic number and physical depth. And phase contrast comes from wave interference and atomic spacing. So diffraction contrast and the wedge, it changes the phase amplitude diagram. So phase amplitude diagram shows how diffracted intensity oscillates as a function of depth through the sample. At a wedge sample with varying thickness causes continuous oscillations between transmitted and diffracted beams, with the crucial parameter dictating the periodicity of these oscillations is your extinction distance epsilon g. So if transmitted intensity hits its minimum at integral multiples of half epsilon g, one and half epsilon g, etc., resulting in alternating dark and bright thickness fringes. And so if we have small s, we have dynamical condition. If we have large s, we have kinetical condition. So in dynamical condition, transmitted and diffracted beams completely interact, and phase amplitude circle is larger, which thickness fringes are widely spaced and prominent. But trade-off is that details of internal dislocations are obscured by a strong fringe pattern. Whereas in kinematic condition, diffracted and transmitted intensities are not assumed not to interfere. Thickness fringes are very faint and tightly packed, and dislocation details are clearly visible in the bright field image because they are not obscured by the fringes. Next is mass thickness contrast. So it is driven by incoherent elastic scattering, that is Rutherford scattering. The mean free path remains fixed, but atomic density alters the electron trajectory. This is a critical contrast mechanism for non-crystalline materials and biological specimens. So if I have a low mass or thin material, there won't be much change in the electron trajectory, but if you have a thicker material or a high Z material, there will be large change in electron trajectory. So atomic number, high Z regions scatter more electrons. Density, denser blocks block more direct transmission. Thickness T, thicker regions force more scattering events even with uniform average G. Next would be objective aperture filter. So the uniform incident beam strikes a specimen at adjacent low mass light gray and high mass dark gray regions. Thicker or higher G areas scatter electrons widely off axis via elastic nuclear interactions. Low mass areas allow higher tighter transmission. So the physical objective aperture catches and absorbs the off-axis electrons. And this results in fewer electrons from high Z region reaching the image plane. So in a bright field image, these regions will appear darker, whereas low mass regions will appear brighter. Next is phase contrast in lattice fringes. So instead of blocking beams, phase contrast relies on collecting more beams through the objective aperture. The higher the number of beams collected, the higher the theoretical resolution. So the tilted so we deliberately allow the transmitted beam and at least one diffracted beam G to pass through the aperture symmetrically relative to the optical axis. This symmetrical displacement G and minus G ensures exact Bragg conditions are simulated, forcing the beams to interfere and create a periodic lattice fringe pattern. So it combines the transmitted wave and the diffracted wave, results in effective deviation parameter. S effective is also square root of S square plus epsilon G square, which accounts for absorption parameters. And this results in sinusoidal oscillation I equals to A square plus B square minus 2AB sine 2 pi G dash X minus pi ST. So the total intensity becomes a periodic wave perpendicular to the beam. So high resolution phase contrast images produce beautiful geometric patterns that intuitively look like atomic planes, but they are not. So you can see in this image they look like atomic planes, but they are not. So they are lattice fringes, which they are interference patterns. They are not direct images of atomic nuclei. What it tells you, the physical spacing between the bright fringes correlates indirectly to the atomic plane spacing of the real lattice. The takeaway is extracting exact atomic positions requires extensive image simulation, not just visual observation. So for diffraction, physical mechanism is beam orientation and exact Bragg conditions. For mass thickness, physical mechanism is incoherent elastic off-axis scattering. For phase, the mechanism is wave interference of transmitted and diffracted beams. Diffraction, the parameters are extinction distance and deviation parameter. For mass thickness, the parameters are atomic number, thickness, density. For phase, the parameter variables are effective deviation as effective and number of beams collected. In diffraction, you see broad thickness contours and visible dislocation lines. In mass thickness, you see darker regions indicating heavy or thick sample areas. Whereas in phase, you get ultra high resolution periodic lattice fringes, which correlate to your atomic planes indirectly. So you will never be able to perfectly produce a perfect specimen with complete uniform thickness. You will have, because perfect uniform thinning is impossible. Every single real world specimen will have some contribution of mass thickness contrast. While we manipulate the objective aperture to optimize for diffraction or phase contrast, mass thickness variation is the underlying inescapable noise of the physical world. So we have to read the image knowing all three forces are always at play. So the final image will have combination from all three and we have to separate accordingly. Now I will be showing you practice questions related to this week's topics. So I don't know anything about the questions that will be coming in your final exam, so I cannot help you with this. But all I can show you is the questions that have been asked by professor in previous year's assignments. The fringe contrast depends on sample thickness, true or false. You can type your answer in the chat. So it is true. So the the change in thickness gives you a fringe contrast. So if the specimen is dashed, only spots will be seen in the diffraction pattern. If it is very dashed, only Kikuchi lines will be seen. Both are thinner, both are thick, thinner and thick, thick and thinner. So the answer is thicker and thin, thinner and thick. So if the specimen is thinner, you will have only spots, but if it is very thick, you will have only Kikuchi lines. Convergent beam diffraction is also called dash beam diffraction, macro, nano, femto. So the correct answer would be nano. So since convergent beam diffraction uses nano probes, it is also called nano beam diffraction. Degree of scattering in transmission electron microscope is a function of dash wavelength of electron beam used, number and mass of atoms that lie in the electron path, mass of the sample. So the correct answer here is number and mass of atoms that lie in the electron path. So that will affect how much scattering is occurring. Mass thickness contrast arises due to dash scattering of electrons. Coherent elastic, coherent inelastic, incoherent inelastic, incoherent elastic. So the answer here is incoherent elastic, which is also called Rutherford scattering. In TM, a higher spot size of the beam indicates lower FWHM. True or false? So this is false because a lower FWHM will result in a smaller spot size, and to get big spot size, we have to increase the FWHM. We can find orientation information through CBED. True or false? So this is true. So the zeroth order Lao zone will give your orientation information, whereas higher order Lao zone gives your 3D information. Deviation parameter S equals 0 is the best diffraction condition to see dislocation contrast in TEM. True or false? So this is false. So the to see dislocation contrast, we should have S greater than 0, positive deviation. If the interplanar spacing in real space is D, the interplanar spacing in reciprocal space will be 1 by D. True or false? So this will be true because the interatomic spacing in reciprocal space is inversely proportional to the interatomic spacing in real space. The Ewald sphere is much bigger in X-ray diffraction as compared to electron diffraction in TM. True or false? So this is false because in X-ray diffraction the wavelength is much larger, so the Ewart square will be much smaller because Ewart square is partial to 1 by lambda. Railroads are formed because a feature in a specimen that is precipitate is elongated in a particular direction. True or false? So the answer to this is true. So as thickness reduces, so a feature is in through the whole thickness, and therefore railroads are formed. So as per information shared by the professor, there will be all types of questions. There will be MCQs, fill in the blanks, one word type answers, as well as long answers. So there will be brief answer questions as well as long answer questions also, where you will have to derive something, or you will have to explain something, or you will have to solve numerically, or you will have to analyze some data. The deviation parameter S is nothing but the distance of the evolved sphere passing through a diffraction spot that is slightly away from the Bragg's position and the exact Bragg position. True or false? So this is true. So at the Bragg position, the vector is G, and at a distance away from Bragg position, the vector is SG plus SG dash, and this distance between G and G dash is your deviation parameter S. Kikuchi lines are formed because of elastically scattering of electron beam. True or false? So answer to this is false. So for Kikuchi lines, first there has to be inelastic scattering of electrons, which are then elastically scattered according to Bragg's conditions. CBED in temp can be used to find lattice parameters of a crystal, true or false. So answer to this is true. So the zeroth order love zone will give you the spots or the circles, which can be used to find the lattice parameters in the zone axis plane, whereas the higher order love zones will give you understanding of the space group, which is a 3D parameter. And the physical distance at which the wave amplitude is transferred back and forth in a crystal is known as extinction distance. True or false? So this is true. So extinction distance is a physical distance of wave between which the wave amplitude transfers between diffracted and the transmitted beam. The dynamic theory of electron diffraction says that there is an interference between transmitted beam and diffracted beam. True or false? So this is true. Dynamic theory assumes that there is interference between transmitted beam and diffracted beam, whereas kinematic theory assumes that there is no interaction between transmitted and diffracted beam, and that there is only one diffracted beam. The Howe-Whelan equations describe the variation in amplitudes of transmitted beam and diffracted beam as a function of crystal thickness. True or false? So this is true. So the Hawley-Whelan equations, which is found a combination of scattering between scattering of electrons from transmitted beam and from diffracted beam is describes the, the amplitude as a function of thickness. Extinction distance decreases with increase in volume of the unit cell. True or false? So this is false. So as the volume cell increases, the extinction distance will also increase. The fringe contrast in a TM image can arise because of variation in thickness or variation in deviation parameter S. True or false? So this is true. Hmm. So this we studied. So if there is a variation in thickness or a variation in deviation parameter S, both will result in a fringe contrast in TM. So this is all I had for today. Thank you for attending. If you have any doubts, you can ask, or if you want, you can leave the chat.